Hello everyone, I'm Xiaolian from Kent State University. Today I would like to talk about our paper, Online Topic-Aware Entity Resolution over Incomplete Data Streams. This is a work with Weilong Ren from Kent State University and Campis Garzino from State University of New York, Canton. So first, let me give the motivation example. There are many existing health-related forums for diseases such as diabetes, non-disease, eye care, and so on. So patients often post their information, such as the symptoms or diagnosis, on these forums in a text format in a streaming fashion. So actually, we can use some existing information extraction techniques to extract some attributes, important attributes from these patients. So for example, we can extract the gender information, symptom, diagnosis, treatment, and so on. However, due to the missing user input or inaccuracy of the information extraction techniques, some attributes from the extracted text might be missing. So for example, here the treatment attribute for the tuple A2 is missing. Therefore, we are actually dealing with such kind of incomplete tuples in a streaming fashion. And also what is more, those patients might post some information to a wrong health group. For example, the user C2 posted his information, his symptom about the blurred vision on the group of eye care. However, the blurred vision might be a symptom of the diabetes instead of the eye disease. So in this case, actually, we would like to identify those comments or messages on the forums, or identify those patients from different forums with the same disease group. For example, we can identify the group of users with the diabetes, and then recommend these, recommend and then suggest these users to some expert or doctors with a diapedia. So in this case, we can formalize this online health community support problem into a problem called online topic-aware entity resolution over incomplete data streams. So for example, here we can consider the incomplete data streams from different forums, and then perform the entity resolution to identify the same set of users or the same set of patients with the same disease, for example, diabetes, and then suggest this group of users to some doctors so that the doctors can give them some suggestions. So this is our problem motivation for the online topic-aware entity resolution over incomplete data streams. So here's an outline of my talk. So first, I will formally give the problem definition of our online topic-aware entity resolution problem. And then we will discuss our solution, followed by the experimental evaluation. And finally, I will conclude my talk. So for the data model of our problem definition, so we will consider the incomplete data streams, where the data arrive in a streaming fashion at the system. And in this paper, we will consider the sliding window model with the sliding window often contains the most recent W tuples. So when a new tuple arrives, we will remove the expired tuple from the old sliding window and then obtain the new sliding window. And as we mentioned just now, the tuples often contain some missing attributes. For example, the diagnosis attribute might be missing. Therefore, we will consider to impute the missing attributes and then obtain a probabilistic imputed data stream. So in this imputed data stream, so each tuple is imputed, and then the missing attribute diagnosis might be probabilistic, might contain some probabilistic values. For example, diabetes with probability 0.8 and conjunctivitis with probability 0.2. So given this data model, so we have our TER-IDS problem, or topic-aware entity resolution problem over the incomplete data stream. So the input of this problem, okay, is a number of incomplete data streams, a set of query keywords related to a topic, some parameters such as the similarity threshold gamma, window size W, the current timestamp T, and a probabilistic threshold alpha. So our problem is to identify the same entity or the same, identify the tuple pairs, okay, from any two of these n data streams, okay, such that these two tuples are matching with each other with high probability, or with a probability greater than the threshold alpha. So this probability is given by this formula, okay, where in this formula we consider two constraints. That means these two tuples must be related to a topic or contain at least one keyword in the query set K, and also their similarity. Well, here we consider the Jaccard similarity function. The similarity between the two tuples must be greater than the threshold gamma. So this problem is very challenging to tackle, okay, because there are three challenges. Okay, for example, it's not that efficient, okay, or effectively to impute the missing textual attributes. And the second challenge is that it's not that efficient, okay, to detect or retrieve the matching pairs, okay, or perform the entity resolution. And what is more, the naive way is to conduct the data imputation, and then we will consider the entity resolution. However, this is not efficient. So our goal is to perform the data imputation and the topic-aware entity resolution over the incomplete data stream at the same time, instead of one after another. Therefore, it's very challenging to tackle this problem. So that's why we proposed our framework, okay, to tackle this problem. So first, we assume that we have a static data repository, okay, so that we can use this repository to do the data imputation. So our framework consists of three phases. Okay, the first one is the offline pre-computation phase. The second one is the imputation and the pruning phase. The third one is the refinement phase. So in the pre-computation phase, so we will obtain some imputation rules, okay, from the data repository, and then we will build the imputation indexes, okay, later on for imputing the missing attributes. And at the same time, we will also consider how to create data synopsis, okay, over the data stream data in order to facilitate the TER-IDS operator. And then for the online phase, okay, so we will consider the imputation and the pruning at the same time. So during the pruning, and so we will propose some pruning methods, and we will also incrementally update our ER result. So of course, at the same time, we will perform the data imputation because those data might be incomplete. And finally, in the refinement phase, we will calculate the actual matching probability between two tuples, and then add the actual pair, okay, to the ER result. So this is our framework. And then for the first, we will consider what imputation method we will use. So in this paper, we consider the conditional differential dependency, or CDD rules, okay, in the form of X determines AJ, where AJ might be missing, is a missing attribute, okay, in the tuple. And also this CDD rule has some distance constraints. Okay, so I will illustrate this CDD using this example. Okay, so assume that we have a table, and in this table we can obtain some CDD rules. Okay, for example, AB determines C, okay, followed by some distance constraints. Okay, so the meaning of this CDD is as follows. Okay, so for the AB determines C, so assume that for the attribute A, okay, if the attribute A of any two tuples are equal to a constant A1. Okay? And then for the attribute B, okay, if the distance between attribute B of these two tuples are within 0.1, so if these two constraints are true, and then the distance, okay, between the attribute C of these two tuples must be within 0.1. So in other words, if this is a numeric value, then if the attribute C of O2, okay, is missing, okay, then the range of this possible attribute C, okay, of O2 must be within the interval between from 0 to 0.2. Okay, so that's how to use the CDD rules to do the imputation. So this is the basic idea. So we can use this CDD rule to impute some missing data based on some existing complete tuples. So in order to reduce the search space of our TER IDS problem, so we also designed some pruning methods, okay, to prune some false alarms. So basically, we will use pruning methods, okay, related to the topic keywords and the upper bound of those Jakarta similarity function, and also the upper bound of the probability, the matching probability, as well as the instance level, pair level pruning, okay, to prune some false alarms of the tuple pairs. So this is a pruning methods. And we also build some indexes, okay, including the imputation indexes and some synopsis over the data stream. So for the imputation indexes, we consider two types of indexes. One is related to the CDD rules, and the other one is related to the static data repository. So the left figure shows the CDD indexes. Okay, so this is an index consisting of two parts, okay, lattice and the AR trees. So actually, we will have the lattice is related to the CDD rules, and the AR tree is related to the actual CDDs. Okay, but we will store some aggregate information related to the distance constraints, okay, in the CDD rules. So since we are considering the textual data in the tuples, so AR tree is usually used to index the numeric data. So we will consider some pivots. We will select some pivots based on the cost model, and then convert from the textual data to the distance between the attribute value and the pivots. Okay, so that's how we convert from the textual data to the pivot to the numeric data, and then store them as aggregates in the AR trees. So similarly, for the data repository index on the right-hand side, or DR index, okay, we also use the AR tree to index the data repository R, okay, and then store some aggregate information in the data repository, okay, with respect to the pivots. And then for the data streams, okay, we also use a grid index, okay, to store those tuples, okay, from the sliding windows in the data streams, and then dynamically maintain this grid index. So essentially, to enable the processing of TER IDS problem, actually we are trying to join these three indexes or synopses, and then enable the data imputation and the ER process, okay, at the same time. In other words, we convert the TER IDS problem to the index join problem. So here is our solution for algorithms. Okay, we will incrementally update the ER results or TER IDS result. Okay, so when a new tuple arrives at the IDS1 data stream, okay, for example, RT, a new tuple RT arrives, so we will remove the expired tuple from the old sliding window, okay, and then we will update the index, the grid index, and the ER result, okay, by removing the expired tuples. And at the same time, okay, we will try to find the matching tuples, okay, from other data streams, and then retrieve the ER pairs, okay, from other data streams, okay, by applying the index join, okay, using the data imputation and pruning methods, okay, with some optimization methods to retrieve the ER pairs. So after that, okay, we will also update the ER results. Okay, so this is a case that a new tuple arrives at the stream IDS1. Okay, for other data streams, the process is symmetric. So here's our experimental results. We tested our approach on real data sets, okay, on 5 real data sets. And here's a table containing some statistics of these data sets. We also compared our approach with 5 competitors, okay, in some existing works, okay, using different imputation methods and using different method with or without indexes. So here's our experimental results in terms of the pruning power for different data sets on the left-hand side. So you can see that our proposed pruning methods can achieve around 98 to 99% pruning power. On the right-hand side, okay, you can see that the imputation accuracy of our approach is around is above 95%, okay, which is higher than some other imputation methods. And here's a result of the work log time for different data sets. So you can see that our approach can achieve better performance than other competitors because we are considering, we are performing the data imputation and the ER process at the same time. To conclude, we formalize the problem of topic-aware entity resolution over incomplete data streams. So this problem is very important in many real applications for entity resolution, topic-aware entity resolution. And we design effective effective imputation methods, pruning method, and indexing mechanism to facilitate this TER-IDS processing, and developed efficient algorithms, okay, via the index joins to enable this online imputation and ER process at the same time. We also tested our approach through extensive experiments on real data sets and show good performance. Okay, that's all. Thank you.